right. Hello, class. Welcome back from spring break. Um, if your spring break was like mine, then it didn't really seem that much different from the week before. Um, and it's probably not going to seem that much different from this week. Um, I did uh, start playing some Animal Crossing, and it's a pretty fun game. Probably played it for like 10 or 12 hours so far. One thing about Animal Crossing I found is that you can only play it for so much every day, right? It's like once you've harvested all the materials on the island for that day, there's pretty much not much else you can do. So I don't know, that's kind of nice. On the one hand, it's nice because then you it limits the amount of time you're in front of the computer game, but then on the other hand, sometimes you just want to play a video game for a really long time. So I don't know. I need another game if I'm going to play for a really long time. Maybe Skyrim or something. Hey, Zach. Hey, Rowan. All right. So today we're going to talk about AC circuits. Hey, Alex. I'm enjoying some Squirt this afternoon. Squirt it's an incredibly refreshing beverage. So, AC circuits. What is an AC circuit? Well, an AC circuit is one where the voltage as a function of time looks like either a sine or a cosine. So a DC circuit is one, I guess I should contrast it with a DC circuit. So for a DC circuit, the voltage as a function of time is just flat, it's constant, okay? So for an AC circuit, the voltage as a function of time is changing. So a couple of things. This is obviously a lot like simple harmonic motion. So there's a period, okay? And 1 over the period is the frequency of the signal, okay? Frequency of your power outlet is 60 hertz. So this period is 1/60th of a second for, hey Aisha, for AC circuits in your home. Then you also have sort of the amplitude. So I'm going to call the amplitude V sub P. The reason I'm calling it V sub P is P stands for peak. So what is the peak voltage? Okay, is another word for the amplitude. So in the case of, I don't have my calculator here. In the case of your power outlet, the peak voltage is going to be, I think it's about 170. Let me check. Yeah, it's about 170 volts. Okay. If we were to go from crest to trough, that's called VPP, which stands for peak to peak. All right. Hey, Justin. So basically, if you want to describe an AC voltage, you need to know what is its frequency and you need to know what is the peak voltage. Okay. Now, we have to also know what is the current as a function of time. Okay? Let me draw a little separating line there. We also have to know the current as a function of time. And if you had a resistor, the current as a function of time is going to look the same way, but it's going to have a different size. Okay. Now, how is the peak current going to be calculated? Well, the peak current would be, according to Ohm's law, it would be the peak voltage divided by resistance. Okay. So that just comes from Ohm's law. So that's for a resistor. For other stuff, so the thing I want you to notice is that for a resistor, the peak of the current lines up with the peak of the voltage. Okay? See how those line up? If you have something that is not a resistor, then you're going to have the same period, but they're not going to line up. So maybe it looks like this. See how now the peaks aren't lining up. So we would say that there's a phase shift between them. Okay. So things like capacitors, things like inductors, they have actually a phase shift. But luckily for us, we're just going to worry about resistors. Okay. So what if we were to graph power versus time? Power versus time. Well, you might recall that power is equal to I times V. All right? Power is equal to I times V. Now, in the case of my voltage could be described as V sub P times, in this case, it's a sine. All right? Hey, Selma. Hey, Stephen. So your voltage is V sub P times sine of omega t. And your current is also a sine. So it's I sub P times sine of omega t. All right? So your power as a function of time is I sub P times V sub P times sine squared of omega t. Now I'm guessing you know what the graph of sine squared looks like. It looks like this kind of. Okay. So you actually, what happens is that when the voltage is 0 and the current is 0, you get a power of 0. Okay. When the voltage is high and the current is high, you get a large amount of power. Okay. So this is what a graph of the power versus time looks like. So you can see the power actually pulses in an AC circuit. It's not a consistent, steady power. Now, you can actually see this. Has anyone ever seen the like super duper slow motion footage of athletes or just super duper slow motion footage of anything? If it's in a room that's being lit by power outlets, you can see this pulsing of the power, and that the lights in the room are actually flickering 60 times per second. Okay, so if you have a super slow-mo camera, you can actually see the light's brightness flickering because the lights are brightest when they get a surge of power. It's kind of cool. Okay. So we can see that the maximum power, the peak power, the PP, if you will, is IP times VP. Okay, that's the peak power. But usually engineers, they don't care about the peak power. What they care about is what is the average power. Okay, so this power, it goes up to a maximum value of I sub P times V sub P. Okay, but what is the average value of the sine squared function? Okay, I'm gonna pause for a second so you can think about that. Actually, I'm not gonna pause the video, but I'm gonna enjoy some more squirt. And I'll wait for someone to type it into the live chat. What's the average value of sine theta? Boo, Selma got it wrong. The average value of sine is 0, but the average value of sine squared is not 0. Zach got it right. So the average value of sine squared is 1/2. Why is that? Because sine squared wiggles between +1 and 0. And it doesn't spend any more time high than it does low. So the average is halfway between the maximum and the minimum. It's 1/2. So the average value of the power is 1/2 I sub P times V sub P. All right. So this takes into account the wiggles. All right. Now, oftentimes this is written. So the average power is 1/2 peak current times peak voltage. All right. Which is going to be equal to, I could write 1/2 as square root of 2 times square root of 2. Yeah, as far as just regular light fluctuation, that's going to have to do with the wiring of your house that's going on in your house. So you might have some kind of issues with the wiring in your house, or maybe the power company, unsteady power from the power company. I don't know. Okay, so notice how we write it as square root of 2 times square root of 2. If I multiply the two square roots of 2 together, we just get the 1/2. Now, when we divide the quantity by square root of 2, that's called the RMS value for that quantity. So I could write this as RMS current times RMS voltage. So the RMS current is the peak current divided by square root of 2. The RMS voltage is the peak voltage divided by square root of 2. So to get to RMS, you have to, to get the RMS, you have to divide by square root of 2. Now, why do we even have something called, by the way, stands for root mean square. And I'm not going to explain why it's called that. You can ask me on Discord if you want to, but it's kind of a pain to explain here. All right. So why do they do that? They do that because notice how in AC circuits, the equation for average power is different from the equation for power in a DC circuit. In a DC circuit, the power is just I times V. But in an AC circuit, the power is 1/2 I times V because of the fluctuations in the amount of power. So what engineers did is they defined a new quantity so that the equation for power is exactly the same as it was for DC circuits. So that's the whole reason for RMS. All right. Okay. So let's do an example and then we'll be done. By the way, the RMS voltage of your power outlets is 120 volts. Yes, I'm saying the engineers are lazy and they don't want to write the 1/2. Exactly. So the RMS voltage from your power outlet is 120 volts. Okay. So as an example, let's say you hook a light bulb of resistance let's say 40 ohms up to your power outlet. You hook a light bulb of resistance 40 ohms up to your power outlet. What is the power dissipated? What is the average power dissipated by that bulb? Okay. Well, we know that the RMS voltage from the power outlet is 120 volts. Okay. What's the RMS current going to be? The RMS current would be obtained from Ohm's law. It'd just be the RMS voltage divided by R. So it would be 120 divided by 40 equals 3 amps. So then the average power is going to be RMS current times RMS voltage, be 3 times 120 equals 360 watts would be the average power dissipated by that. Okay. Like it got dark all of a sudden. All right. And then also, one way we could extend it is you're also going to notice that the lights are blinking. The light is blinking. If you had a super fast camera, you would notice that the light is blinking. What would be the period? What would be the time between each blink of the light? And if we look at it here, notice how if we squared the voltage signal, notice how this negative becomes a positive. So when we square the signal, see, this is a full period right here. So the blinks actually happen twice as fast as the frequency of the voltage signal. So basically, if the voltage is coming in at 60 hertz, then you're going to notice that the light blinks at 120 hertz. Okay. I think that's kind of neat. So, different countries have different standards for their voltage of the power outlet. I think that Europe has a higher voltage than America does, and I'm also not sure about the frequency. I don't know what the frequency of Europe's electrical grid is. Someone should look it up and let me know. All right, that's my lesson for today. Hope you guys have an awesome rest of the day. I'll see you tomorrow.